Understanding the quality or dryness fraction is key to using saturated tables effectively. The specific volume of saturated liquid and vapor are crucial parameters, and the difference between them helps determine the dryness fraction, which is essential for calculations involving steam and water mixtures. To use tables effectively, first determine the dryness fraction, X. This allows you to calculate average values for specific volume, internal energy, enthalpy, and entropy. The equations provided help in finding these averages, which are essential for accurate thermodynamic calculations. Superheated vapor exists above the saturation temperature at a given pressure. Using superheated tables, you can find properties like enthalpy and entropy for superheated steam, which are vital for processes involving high-temperature steam. In 1662, Robert Boyle discovered that the volume of a gas is inversely proportional to its pressure at constant temperature. This fundamental principle, known as Boyle's law, is a cornerstone of gas behavior understanding. In the 1780s, Jacques-Charles found that the volume of a gas is directly proportional to its temperature on an absolute scale, at constant pressure. Charles's law complements Boyle's law in describing gas behavior. By combining Boyle's and Charles's laws, we derive the ideal gas law, which relates pressure, volume, and temperature of a gas. Including the gas mass, this law becomes a powerful tool for predicting gas behavior under various conditions. The ideal gas law is often expressed as PV equals nRT or PV equals RT. It can also be written in terms of moles, providing a versatile framework for understanding gas properties and behaviors in different scenarios. Using the molar mass of a substance, the ideal gas constant can be calculated, which is the same for all ideal gases. This constant is crucial for applying the ideal gas law across different gases and conditions. Specific heat capacity is the energy required to raise the temperature of a substance by 1 degree. For gases, it varies with pressure or volume, and is measured at constant pressure or volume, reflecting the energy needed for temperature changes. In reversible processes, the heat transferred is calculated differently for constant volume and constant pressure. These equations are essential for understanding energy changes in thermodynamic processes. Joule's law states that the internal energy of a perfect gas depends only on its temperature. This principle is fundamental for analyzing energy changes in processes involving ideal gases. Work done at constant pressure is given by the product of pressure and volume change. The relationships between specific heats and the gas constant are crucial for understanding energy transformations in gases.